Okay, so today we're going to talk about composition of functions, and we're also going to talk about translations and transformations of functions. Okay, so a function, we take a composition of a function is where we're going to take the output of one function and we're going to make it the input of another function. So the notation here is that I'm going to take my function g at x, and whatever comes out of there, I'm going to put it inside of f at x. Okay, so this can be a useful or not so useful way. Okay, so if I were to make this, an illustration of a machine, if my machine changes my x to g of x, I'm going to put this machine, put my x through this machine, take the output of that, put this through this machine, and we get out the composition like this. So let's say if we have two functions, one of them g at x is x plus 2, the other one is f at x equals x squared. If I put in a value, let's say if x equals 3, that means 3 is going to go in here and we're going to get a 5 out of there because I'm adding 2 to 3. And then I'm going to take that 5 and I'm going to put it in f, and so I get 5 squared, which is 25. So f composition g at 3 is 25, is the way you would read that. Okay, so let's say we have a function that's a table here. And so we want to find f at 3. This is easy enough. We just look at 3 and we get f at x equals 1. All right, so if we look at g at 1, 1 is 3, right? So g at 1 is 3. If I take g at f at 3, so the output of f is going to be 1, so it's going to be g at 1, we get 3. So what we have to do is we have to use one table first and then use the output of that one as the input of the other one. Now it gets confusing, and I purposely made it confusing with just 4 numbers in 4 different columns, so you have to kind of trace through it and just slow down a little bit, and you say, okay, if I want to find this, I first evaluate this. The argument is the x, so that's 3 gives me 1, and then I have g at 1 equals 3. Okay, so try this one. What do you think?
1.
I'm sorry? 1, right? F at 2 is 2. G at 2 is 1. Okay, and if I do it this way, f at g at 2, g at 2 is 1, f at 1 is 4. So you have a few problems on your homework that will look like this, reading tables. Okay, and where this practically comes out is oftentimes what you have is data that comes from 2 different places, and you have to cross-reference one to the other. For example, if you have a table that will from the U.S. Government Census Bureau that maps something like what's the percentage of let's say Hispanics in California. And then you have another function that tells you about Hispanic values, like in a certain survey, Hispanics think 40% one way and 60% the other ways. Then you can ask, the question, what's the result of Hispanics in California? So you're using 2 different functions to get to an answer that's actually a blended version of those 2 functions. Okay, so let's go back to an algebraic definition. Let's say we have 2 functions like this, where we have f at x equals x squared minus x, and g at x is 2x plus 1. If we want to do this composition, this function of f at g at x, this is going to be the same thing as f at 2x plus 1, right? Because g at x is 2x plus 1. So what you're going to do then is you're going to write f at x but instead of writing x, write parentheses, and just drop in there whatever you have for g. And so when I write in what is in g, and then I extend it and simplify it, this is the composite function. So really what I have now is I have f composite g is 4x squared plus 2x. And so now all I have to do, well, let me go through the steps here if I were to do it individually. Let's say g at 2, we want to do f at g at 2. So g at 2 is going to be 2 times 2 plus 1. 2 times 2 plus 1 is 4 plus 1 is 5. And then I'm going to take f at 5 and say, okay, 5 squared minus 5 is 20. But if I had already combined them like this, I can just go ahead and put in my 2 in this function, and I get 4. I'm using this particular expression now, 4 times 2 squared plus 2 times 2, and sure enough, I get the same thing. I get 20. So composition of functions is really important. You know, you can piece together functions. The way we're going to look at it, though, is we're going to look more from a calculus standpoint as decomposing functions where we can identify the composition of functions, because we'll find that you have certain rules of differentiation and integration that work with things like your toolkit functions, and we'll be able to make a use of simpler rules on more complex kind of functions. So just actually combining them like this is used probably less than actually decomposing them, if you want to use that word. Okay, but here's one for you to try. Let's say you have f at x equals 1 over x and g at x equals x plus 1. I want you to find f composite g. Everybody has it? Okay, let me go through how to do this and see if you did it the same way I did it. All right. Make sure you sign in, okay? Okay. Any questions with this one? You see how that worked? Where I put the function g in as the argument of f, and so when I wrote f is 1 over whatever this is, I get 1 over x plus 1. So this is a fairly straightforward one, but there's as they get complicated, let's look at this one. How would we do this? We could do it the same way. We can say, okay, we're going to have g on the outside and put 1 over x on the inside. And so what we're going to get then is this value is this x, and so we have 1 over x plus 1. So the order that you do these matters for most unrelated functions. Okay, let's take the composite of itself now. Okay, how does this go? 1 over x, which is just x, right? And how about g composite g?
X plus 1 plus 1.
Plus 1. So we get x plus 2, right? Okay, so how we're going to use this. I mentioned this before, but in calculus we're going to do this by identifying functions as composites of functions. Okay, so maybe I have rules for how to deal with the square root, and I have rules for how to deal with addition. So I want to essentially make this into two functions. So there's always a number of ways to do these, and so you have to kind of develop a vision for what will be useful and what will be less useful. Okay, so on this one, I can say, if my two functions are g composite h, I can say, okay, g at x equals 2 plus the square root of x, and h at x is just x minus 1. You see how that works? Because if I do g composite h, that means where x is here, I'm going to have an x minus 1, so that translates into 2 plus x minus 1. I made a composite. So here's two things going on. One of them is I'm taking the square root of something and adding 2 to it. The other one is I'm just subtracting 1. And so I'm looking at this thing as I have this inner function here, and then I have this outer function, which is that first function that's listed on the composite statement. Okay, but it's not unique. Okay, when you actually combine two functions, you'll get something that's unique. But if you're taking things apart, there's more than one way to take things apart. So an alternate would be, let's just have 2 plus x, and my other function is h at x equals square root of x minus 1. And so when I take g composite h, okay, it falls out naturally that way. So depending on what you want to do, you can decompose these functions in a number of ways. And in fact, we can make it 3 functions, the composite of 3 functions, right? We can make one function this, the next function is just the square root of x, and then the third function, the innermost function, is x minus 1. And so that's going to be very, very useful because we'll be able to make substitutions, and for rather complex functions, we're going to be able to apply rules that pertain to very simple functions. Okay, so here's one for you to try. So I figured at least 3 solutions on this one, and there's perhaps more, but decompose these into 2 functions, okay? Okay, let's have a couple people suggest what they've decomposed it into. Okay, so let's call the 2 functions g composite h at x. What would g at x be, and what would h at x be?
X minus 1.
X minus 1 would be which one?
G of x.
G of x would be x minus 1, and h at x would be then?
Square root of x.
Yeah, think about how that would compose itself. It wouldn't be where you want it. Now, since I wrote it this way, where the g is first and then the h is second, g is the outer function, okay? It's not the inner function. So 1 over x would be one way to do it, and then what would h at x be? Right. Is that minus 1? Not plus 1. Okay. Okay, anybody else have one that's a little different? That's one possible solution? Yes.
For g of x, I have 1 over the square root of x.
Okay, and then h at x is?
X minus
X squared minus 1, right? See how that's, now when we put that in here, we get the original function. Anybody want the third one?
1 over the square root of x minus 1. And then x squared.
Very good. Okay, so these are separate definitions there. All right, so let's see what I got here. And I think I got those 3 versions of it. So this was the first one I'm listing there. This one is the second one, and there's the third one. We're going to learn something called the chain rule, which is a way to differentiate something where you're going to be looking at inner functions and outer functions like this. And it's really going to be not a matter of even giving them names, it's how you're going to address a certain function. Okay, so let's change subjects now and go into transformation of functions. This is section 1.4 in your textbook. And so what I want to do here is I want to use our toolkit functions. Remember that those are those handful of functions that are relatively simple to envision, like x squared and 1 over x and things like that. And we want to build some new functions by modifying these functions, by moving them around and things like that. So that's going to be the point of all this. So what I wanted to use first is the absolute value of x. Okay, so this function should be, pretty much in your brain, where you have a straight line with slope 1. When it's greater than 0, when it's less than 0, it has a slope of -1. So when x equals -1, the absolute value of -1 is 1. Okay, so let's say I'm going to take my f at x, which is my absolute value function, and I'm just going to add 2 to it. And so if I make my table, I have x and the absolute value of x. And then if I add 2 to the values of f at x, this thing is going to move up. Okay, so if I take a function and add a constant to it, I'm moving that function either vertically either up or down, depending on the sign of this thing. So that'll be our first translation rule, that we can take a function, add a constant to it, and it goes up or down. So we're going to generalize these things as we go along. So we're going to say when we add a constant, it moves it k units, up or down depending on k's sign. Okay, so now let's say I'm going to subtract 2 from the x. So this is the innermost function, right? Is I'm going to modify x before I do anything to it. So here's my f at x, and if I take g at x, which is this, I need to subtract 2 from this. So this is -1 minus 2, and then the absolute value is 3. If I'm at 2, then I'm going to say x minus 2 is 0, and so the absolute value of 0 is 0. So look what happens here. If the black is my toolkit function, f at x minus 2, so if I subtract 2 from the x before I perform my toolkit function, I'm moving it to the right. Okay, so this is negative here. So let's generalize this one. Now we have to be careful about how we assign positives and negatives, because it was easy when positive is up and negative is down. That's intuitive, but this one may not be so intuitive. So I'm going to call this h negative, and I'm going to say it moves it to the right h units. That means when h itself is negative, that means it's going to be x plus some value of h, and it's going to move it left. Okay? So when you see a minus sign, you're going right. When you see a plus sign, you're going left. Okay, so that's a little bit backwards than perhaps you would guess if you were, before you actually thought it completely through. Okay, so now we have another toolkit function, x squared. So the vertex of this thing is at 0, 0. And so what I'm going to do is I'm going to say, let's say I have this function g at x minus 2 squared plus 3. Can I expect what's going to happen here? Compare this to our toolkit function. What's going to happen? Yes?
It's going to go horizontally to the right 2, and then it's going to go up further.
Up 3, right. Okay, great. So it's going to look like this. Every point that's associated with this is going to move up those values. And so the easy way to do this schematically is take your vertex and start your vertex here, because it's to the right 2 and up 3, and then draw your sketch around it. I guess I made a correction on there. Oh well. Okay. So you try this one. Make this sketch in your notebook. I'm going to use the toolkit function, the square root of x, but what I'm going to do is I'm going to add 3 to x and subtract 1 from the function. So how is that going to look? Okay, so I'm corrected there. And that's -1. Double corrected. Okay, everybody okay with that? Okay, so let's look at now making a graph where we're going to apply a negative sign to a function and see what happens. With our absolute value, we're going to get, just the regular old toolkit function. What happens with when we apply a negative to it, it actually is mirrored with respect to the x-axis. So it's just flipped over. Anything that's positive is going to be negative. Anything that's negative is going to be positive. So it flips over like this. And so that's a fairly easy one to generalize. So this just means that it's a vertical reflection. Okay? So now this one's a little bit more complicated. If I make my x negative, that may work, right? But it may also have an impact on the domain. Because notice here that your domain, x has to be 0 or more. Here, it has to be 0 or less. Because if x is -2, then we need -2, and we get the square root of 2, which works. And so oftentimes you have to extend this table where you say, okay, I can do this 4, 1, and 0 conveniently. I can take the square roots of those, but I can't take the square roots of these. But since I'm doing a reflection here about the y-axis, I have to transform my domain to be the negative of the domain that I had before. So these values work, and if I draw that as a graph, you'll see that this is my original domain, or this is my original function, and you see the domain is 0 or more. The reflection is going to be about the y-axis, and since I'm changing values on the x-axis, I have to pay attention to the domain, and so my domain now is going to be all negative numbers. So here's my rule. So if g of x equals f at -x, g at x gives a horizontal reflection, so it's about the y-axis of that. Okay, so let's look at a little algebra on the toolkit functions x squared and g cubed. F at -x, you'd expect it to be a horizontal reflection, but think about x squared, it's symmetric about the y-axis, right? So just because I take the negative of it, if I take -x squared, that's still x squared. So I have f at -x equals f at x. That's characteristic of this function. If I use x cubed, and remember what x cubed looks like, well, when I cube -x, I still get -x cubed, so it's going to be -g at x. So if I take -x here, I'm actually going to get a reflection, because think about the way the x squared is like this, and so when I give that kind of reflection, nothing changes, but x cubed, think about the toolkit function here, like this. If it's flipped like that, I indeed get something that's quite different. And I even actually draw that. So there's f at x equals f at -x, and here g at x and -g at x equals g at -x. So we're going to call these, this is an even function because this relationship holds. This one is an odd function because when we take this negative, it's going to be negative here. Now, here's an assist from the toolkit function, is that how can you remember what's even and odd? Well, remember x squared, the 2 is even, so if it behaves like x squared, so f at -x equals f at x, that's an even function because your toolkit function is x squared. Your toolkit function that shows this, where -f at x equals f at -x, that's an odd function. Of course, functions can be either even or odd, or they can be neither. Probably most functions are neither, right? They do something else. But these have a special characteristic that we call even and odd functions. Now, there is no function that is both even and odd, okay? Try as you might, you won't find one that's both even and odd. I suppose the function f at x equals 0 is both even and odd, because f at negative x equals 0, and negative x equals negative 0 as well. So that's a trivial function. No substantial function can be both, right? Okay, I'm not going to go over this class exercise. What I'm going to do is I'm going to assign this as part of your homework. And I'd like you to look at these functions and see how they compare to this function here. So in this one, I'm multiplying the function by 2. In this one, I'm multiplying the variable by 2. This one, I'm multiplying the function by 1/2. And this one, I'm multiplying the variable by 1/2. And I'd like you to make the generalization rule now. What happens when you multiply a constant times the variable or a constant times the function? And I'll tell you what the answer is. You just have to sort out which direction it goes. One of them either stretches or shrinks the graph as though it was written on a piece of rubber paper that you would stretch, or Play-Doh. Did you ever use, not Play-Doh, silly putty? Did you ever make those, with the newspapers? You can, if you stamp it on newsprint, you get it so you can stretch, the print. Okay, you know what I'm talking about. I'm not that old that we have some overlap in this. Okay, and then the other one, and it'll be this one, that either stretches it vertically or shrinks it vertically. So this exercise, which will be part of your homework, I'd like you to make those graphs. Okay, and what you should end up with is something that looks like this, all right? Yeah. It'll be online, okay? What will not be online is this, the solution, okay? But I'm showing you what the solution should look like, okay? So if you have a photographic memory, but just make sure that when you first plot this, and I'm only asking you to do x between 0 and 4, you're going to get a graph that looks like this. And then these will be various shapes similar to it, and then you can see which ones stretch and which ones contract. Okay? Can I go on now? Everybody has it? So it'll be online, and I'll remind you in the homework to look at slide, whatever this is, whatever number this is, and do that exercise. Okay, so you'll end up with a rule like this about stretching and compressing, and then also the horizontal stretch and compress. Okay, well, let's look at this right now. And I'd like you to take a few minutes with this one to try and decide, what does this one look like? Okay? Looks like a pretty ugly function, right? I mean, nothing that you would necessarily guess at. But let's go through the steps of this and see how can we get this thing to look properly. Now, you're going to go through the exercise of this. Imagine this as 1 over x, right? Or one of your toolkit functions is 1 over x squared. So that's the one that you need to start with. And then this is going to be multiplied by -3. So with the 3, you're going to get a stretch or a shrink. With the negative, it's going to be inverted. And then with the -1, it's going to move back and forth this way, and with the 2, it's going to move up and down. So if you break these down into individual operations, okay, we're going to start with this one. This is kind of at the core of all this, is something over some variable squared, right? And so then if we do this, if we multiply this function by -3, we get a vertical reflection, and we're going to stretch it by 3. So if we get, and I will be drawing this in just a moment here. So it'll be a vertical reflection stretched by 3. This next one here, if I put in this x minus 1, I'm going to move to the right 1. And then the next thing is when I add 2 to it, okay, so here, notice I'm keeping my function. I'm going to shift it up by 2. So then let's see if I draw this thing properly. Okay, so here's my f at x squared equals, it should be 1 over x squared here. I got another mistake. Oops. Okay, so there's my function that I've graphed there. So then, if I look at what I've done here, first thing, I've made a vertical reflection, so this thing is upside down. Then I made a stretch by 3, and on this particular one it's hard to show. Okay, so we're just going to imagine this thing is stretched out by 3. I'm going to move it to the right by 1. Okay, so I'm going to move what this axis of symmetry is. I'm going to move it over to 1. And then I'm going to move the whole thing up by 2, and so I get this thing that looks like this. Now, it's not drawn very precisely, but the point here is to make a change so we have, you know, a conceptual idea of what it looks like. So when you're looking at this graph, or when you're looking at this function, it doesn't come to you right away, but just, you know, break it down. Okay, I know what 1 over x squared looks like. I know with a -3 as a coefficient, it's going to stretch it out, and it's going to flip it over, and then the -1 and the +2 is going to move it. It's going to move it this way 1 unit and up 2. So with a little bit of thought, you can say, okay, you can imagine your toolkit function like this, and then flip it over and move it over, and that's what your function is going to look like. Now, we're going to spend a lot of time in this class learning how to sketch functions. And there's another approach that we can use to this particular one that we'll be using at some point. Actually, 2 more approaches. But this is one that, you know, just from a breakdown of what your toolkit function kind of shows you what's going on. And I think the important thing to recognize here is that when I have 1 over x squared, that they run off to infinity in the same direction. Okay, 1 over x, remember this function here, looks like this, where as you get close to 0, depending on whether you're coming from the negative or the positive side, it's going to run off to either positive infinity or negative infinity. So this is to me one of the most important concepts that you can get in terms of understanding what functions do, is to look at a few basic functions and see if you can kind of take another function apart and understand from its core what it's going to do. Okay, that was pretty fast, right? Okay, so any questions on this?